Okay, so hello everybody, welcome back to our whole training series. Today I'm very happy to introduce Matthew Kravchuk, who is a research scientist at the National Center for Supercomputing Applications. And Matthew is going to talk about the framework that he has been developing for the past, I guess maybe already closer to a couple of years. And this framework is designed to sort of simplify the code reuse and to put together multiple frameworks to work to help you to develop models without reinventing the wheel. And so, Matthew, we are very happy that you are able to talk about your framework. And this framework is enabled to work on our whole system. So you are welcome to start using it after this tutorial. And so, Matthew, please take it on here.
Thanks so much, Vlad. Yeah, Vlad said it pretty succinctly. DRYML, it's an acronym meaning don't repeat yourself machine learning, the typical don't repeat yourself adage in programming where it's not good if you're rewriting the same method over and over again, which I've often found myself doing running various machine learning projects throughout my career here. And so when I started writing this library, I have a couple of goals, which was, first of all, I want to reduce the duplication of code. Like, I don't want to have to be rewriting the same training methods over and over again. I want to make it easier to serialize models. So often when we write models, we create classes to represent them or have methods which help loading and unloading data that are specific to particular models. Maybe they're different depending on maybe you change your model a little bit and that requires you to change the input data format. I found it really difficult to maintain libraries of heterogeneous models, you might say, heterogeneous models, where each one may have a different requirement for data processing. Another is easier hyperparameter searching. So there are a number of platforms for doing hyperparameter searches out there, but they all have their own ecosystem. You have to try and fit your system, your model within their environment. I liked Ray the best, so once I had developed most of the framework here, I created some adapters to basically fit DRYML models into the Ray framework. I wanted to employ composition-based development of models. So a problem I found in my own work was if you change your model a little bit or you want to use a new method for training, oftentimes those are attached to some class. And with the composition method, you separate those implementations from the class themselves. The idea is that your model is kind of like an entity, and you attach functionality to it with components. This is often used in game engines, and I felt it was useful here as it would prevent me from having to rewrite new classes if all I was doing was changing one component of the class. So basically, that means if you're creating a training method that works for a large variety of your classes, you just have to write that method once. And you don't have to worry about complex inheritance hierarchies or anything like that. Another issue that I ran into was dataset APIs. Every single framework has their own specific way of doing things. So the goal was, if I want to make these frameworks work together, I have to create some uniform API that they can all fit in. So I made my attempt to write an API, a dataset API with so adapters to the various machine learning frameworks, and it should allow you to reuse transformations that you might write in one framework within another framework. So there are a couple of important components that one of the design philosophies I came into writing this library was that you should only, if you want to use a piece of it, you should not have to, like that, you should be able to get to use that piece without requiring you to bring in dependencies like TensorFlow. Like if you're just wanting to use the ability to serialize objects, there's no reason that you need TensorFlow for that. So every bit that requires, most pieces of this library are sort of separable in their own little submodules, and you should be able to take what you need and leave what you don't. So the first major component are the sort of foundation of DRYML, which are objects, object definitions, the repo, and selector. And the point of these is to facilitate serialization and the creation of what you would call object factories. The idea being you can define a kind of object and then easily create new versions of that object. And the repo and selector form a basis for searching. So if you're doing an experiment, machine learning experiment, and you've got, you're doing a hyperparameter search and you've tested maybe 1,000 models, it's sometimes difficult to find the right one. Like, what's the best model in the group? Okay, maybe you can do that once, but once you start doing this multiple times, your notebook can quickly become quite hairy, and your directory structure quickly becomes quite hairy. You're creating, directories with very specific names, like dates, including when you ran the experiment and exactly what the parameters of your experiment were. It's a real pain. So the point of the repo is to allow you to directly specify properties in the notebook that you're looking for in a model, and then the selector is capable of going through that repo and grabbing just the objects it's interested in. I mentioned already data sets. So the dataset component of DRYML is, again, separable from the rest, so you can just use that part if you like. Then there are compute contexts. This is an idea, if you want to specify the way a framework uses a device, each framework has their own method of doing that, which can become quite a pain. And I found especially, I have a machine at home with 2 GPUs, and one of them is meant for drawing the screen, and the other one is meant for doing model training or something like this. So every time I'm launching a training session, I have to tell TensorFlow, don't use the first GPU, use the second GPU. Otherwise, my desktop slows down and I get like all kinds of artifacts or something like that. So I found having to input a block of code at the start of every notebook, and that was starting to get me annoyed. So the goal of a compute context is to sort of unify the way this is done to one line that should work for all frameworks. Unfortunately, this isn't. It works well more or less for TensorFlow because TensorFlow has a lot of tools built in for this, but the goal is once more tools are available in other frameworks, you can expand to that as well. But this is, the idea of compute contexts, those again are separable. So you can pull that piece, that submodule out of DRYML and use that in your workflow. You don't have to use every other piece. And finally, there's trainables. These are combining many of the different, like the previous concepts into a full machine learning framework. So you can compose a model of different, build it up with different components. There are implementations for major machine learning frameworks, and with a uniform dataset API, you can chain together different models into one pipeline. And that way, if you want to, say you had a pipeline you got working in TensorFlow, and now you want to try it in PyTorch, you don't have to go back and re-implement your MNIST or whatever data set that you've got coming in PyTorch. You can just use the existing one and then use the dataset adapter to change it from TensorFlow into PyTorch. So these are the important coordinates here. First, it's a GitHub repository, so it's NCSA/DRYML. There's some documentation there. If you have problems with using it in your own work, please raise your issues, and I'm happy to interact. And if you have PRs that can improve functionality, I love it. I would love to integrate some PRs. It's released on the PyPI, so if you want to use it in your own work, you can just say pip install DRYML. And like I mentioned, because each component is trying to be as isolated as it can, the basic components of DRYML don't require basically any dependencies at all. So in almost any project, you can say pip install DRYML and you can just get going using the most basic parts of it. Now, if you wanted to use TensorFlow implementation, then of course you're going to need to have TensorFlow available. So to access it on HAL, currently we're using the HAL training reservation. So if you're going through on demand, make sure you input the HAL_training for your reservation. It's already installed in the OpenCE v161 environment. So when you're launching a new notebook or you're opening up the tutorial notebooks I have, you make sure you change your kernel to this OpenCE v161. So how to access the tutorial material? So I recommend cloning the DRYML repository in your directory and then changing to DRYML/tutorials. That's what you'll find all the notebooks in there. I guess another thing you could do is you could navigate through your web browser to this repository, this GitHub repository, and like physically download each one. But I think that'll probably take longer than doing git clone. All right, so I've got like 6 notebooks, each with like 20 or 30 cells. So let's just see where we get, and hope everything goes smoothly. Okay. So this first tutorial is all about objects and their repositories. So, we got our preamble up here. We're just grabbing object, save object, load object, repo, and selector. So the thing to remember, the thing about these are the most important classes in DRYML. Object is a kind of meta class, which, well, sorry, it's a base class you should inherit from if you want to utilize DRYML. And object uses a meta class to enforce an API. And basically that API is, it remembers how you've constructed the object. So this is a little UML diagram. Let's see, I should subtract. Yeah, there we go. This is a little UML diagram showing how things work. So on the left side here, we've got object, and maybe you've got a user-defined class, which is inheriting object. So you may have attached your own user data to it, and maybe your own methods to it. The underlying object will record when you create when you call the constructor, it will record the arguments and KW arguments that you use to create it. In addition to that, it'll create a DryID. It'll create a DryID KW arg, and it'll create a metadata dictionary. And that will include a description, and also I think it does creation time as well. And it comes with a handy function called definition. And then when you call a definition function, it returns an object def class. And object def is just containing the metadata about your object, what arguments you use to call it, and that's it. So it doesn't, if you have a model that, let's say you have a GPT-3 type model in this object, and you have 30 gigabytes of parameters associated with it. When you call that definition, you just get the very top level metadata that you use to create it. Maybe like the number of layers you used if you expose that in the constructor, for example, or like I don't know, like the number of filters or the number, how big your attention layers are or something like that. If you expose that in the constructor of your object, that will be available as information in the object def, but none of the other crap. So that way you can search a directory full of these without having to load them all into memory. Okay, so let's show how it works. So we're going to create a very simple object and just poke around here. So the thing to remember is DRYML is creating, like you specify this class like you would a normal Python class, but there's a class called meta within DRYML, which is going to change your init function. It wraps it in a larger init function, which does all kinds of fancy things like remembering which parameters you used. But importantly, this means you're not supposed to call super within this init function. the one that meta wraps your function in does all that super stuff for you. So don't worry about super. This is already handled for you. So if you're doing a inheritance hierarchy, you don't have to worry about super getting called. It'll get called automatically. Okay, so what we did here is we just create a new object data, and here, this init function is not doing much. It doesn't look like it's doing much. I'm just passing here, but importantly, it's recording the which parameters the constructor will take. So when DRYML sees this, it will say, okay, this class will take one parameter. So now when I create a new object, that's a data object, okay, it will remember how it gets constructed. So if I inspect its dryargs parameter, you'll see there it is. It remembers the arguments were a tuple with one element, and that element is that array that we passed in. And it also will remember KW args if you passed them. In this case, actually, that wouldn't. In this case, it wouldn't really work because it'll know. DRYML will notice that you didn't pass. You didn't plug in like args here. So if you add extra arguments, it'll complain. And if you did this, it'll also, you have to put a wrapper up here for them to make that work. But the point is, if you add extra parameters here that aren't handled by object underneath, then you'll wind up with an error because the DRYML will see, if you construct it with additional parameters, it'll see those additional parameters and not know what to do with them because the signature of this init function doesn't include that. But for now, we're just going to do that. Just have one argument. But here, it's adding a couple extra arguments. First is the dry ID. This is a unique ID for your object. And this is really useful, especially when you're doing machine learning experiments. Because when you usually, when you create a machine learning model, like a deep learning model, they're often initialized with a random state, and then you use gradient descent to train them. This way, you can create new copies that are maybe different initial states, and then you can train them. On different or the same data and see how their performance changes. Like, how much does randomness affect your model's performance in the end? So we also include descriptions in the metadata. So if you want to say like this is trial, training trial 1 or something, like this model is from training trial 1 or something, you would put that in description. You can also add additional keywords if you want. And then of course there's a creation time, so you can search based on like, well, I remember, I created that model on Tuesday, so let's look at all the models I made on Tuesday. You could do that kind of search as well. And yeah, I include here a little bit of code to convert that into a more readable timestamp, since there's currently the implementation I'm using is a Unix timestamp. Okay, so we've got an object. It was really easy to make an object that uses DRYML up here. We just had to inherit from object. Now what? Okay, I can get a definition from it. So I can say object.definition, and here you get this dictionary looking thing. It's got the class. This dry mute thing is kind of, it's a legacy thing. I think I need to get rid of it. But originally I had this idea that certain objects you couldn't change and some you could. I'm not sure. I might extend that in the future, but for now it's sort of just floating around here. Then you've got dry args. These are the arguments you use to create to call the constructor. You've got KW args. These are arguments that were passed and could be passed, or were passed or could be passed to the constructor as well. So if you don't pass dry ID, the object-based class will create it for you, and same with description and creation time in the metadata. So here's where you can use the factory component of the object definition. So let's say you have an object and you want to create a new version of it. You can just get the definition, and then you can use the build method. So this will create a copy essentially of the object. It'll construct the object in the same way that you constructed it originally. but it'll be a different object. So we can copy it like this, and then we can check that the definitions are equal. So if they have the same definition, the equal sign is implemented for this definition type. But you'll notice they are different objects, so their Python IDs are different. But we can edit the definition and remove the unique ID. So let's let's get that definition here and take a look. So we can see, right, we've got dry ID here, and we've got description and creation time. I built a convenience method called get cat diff in that def, and that's the point of that is get category definition. I didn't want to write category every time, so I shortened it to cat. And the goal is like, we're going to strip out all of the unique data about these definitions, and that way you don't have to worry. You can just use that definition to create a new object that's very similar to the, has all the same structural elements, but they may contain different versions of that of those objects. So if we get that cat def and take a look at it, you'll notice that all of these little bits from KWRs are gone. So there's no dry ID anymore. There's no creation time anymore. There's no description anymore. So this is sort of like a blank canvas. And then if we use the build object now on that category definition, you'll see it's a new object. It's got a new ID. So this one's 90E over here. It was B93. So these are different. This is a new object and to DRYML. And it's got a new creation time and a new description. Well, in this case, we didn't pass a description, so it's empty. But we could conceivably come up here and say, right, we could go like, let's see, try metadata. Let's see if this works. No, I think I have to go like this. To remember, how does it work? Yeah, there we go. Right. So now I've changed it. So I've added a description test to this, and now we can create a new copy. And now you'll see that the description is set to test. Okay. So now we've got this object, and we can see that you can get definitions from this, and those definitions can be used like builders or factory methods. So the next step would be serializing and deserializing. So to start, I did all this implementation using a zip file. So that's something you guys should just be aware of. This is not something you're going to be storing, an 80 gigabyte model in probably. Zip is currently implemented in Python. I think it's all in memory, so you don't really want to do something like that. These are kind of for, you might say, mid to small size models right now. Each object has a helper method called save self, and then it takes either a path or a file-like object. So you can even use like a bytes.io stream or something like this. But for now, I can say use object. Right now I chose the .dry as the ending for the file. But when you call this method, all of the data about that object, so the metadata is saved to disk, saved into the it's essentially pickled and then saved into a zip file. And now you don't have to use a constructor. So like you don't have to remember how that object was originally made. you can just use the load object method. So before I imported the load object method, we just passed the name of the object, or you can use a file-like object will work as well. And it will load a new copy of that object from disk. So they're nearly indistinguishable and they contain the same data, right? But they're actually different objects. So if I go like this, yeah. I think I'll just do an insert here. Yeah. So it loaded the same data from disk, but they're actually, it created a new object when it did that. It followed the instructions in the definition to create the object, and then it used the further loading methods to load the data from disk. So that's the next topic. What about storing data? So we've done the basic steps of saving and loading arguments and like args and KW-args and stuff. Those are all enforced to be pickleable, essentially. So the class which wraps the components that handle the args and KW-args will check to see whether or not the object, whether or not the item you used in the argument or KW-args is something like a plain data that can be pickled. But let's say you want, you have some data that's coming with your model you need to save. That's where the save object implementation and load object implementation comes in. So this is something that your user class will need to override if you have extra data. And I mentioned that there's implementations for major ML frameworks, and in those cases, I've handled these implementations for, let's say, I think TensorFlow, PyTorch, and sklearn. But to give you an idea how this is working, consider this is a sequence diagram. So here we have a class hierarchy. This object's the base, and then we've got, like, say, 2 user classes which are inheriting it. So you call load object on the, on the actual like file path. And what happens is you enter the load object class, which is managed by the this is created and managed by the meta class. It handles creation of a bunch of extra helper functions, one of which is load object. Essentially, it'll go down in class and then go down in class, so till it gets to the base, and then it'll go back up, and then that class will load its data. So that's where your implementation comes in. So the user load object imp comes in, then the user data for this class gets loaded, then it goes up, and the user data from the next class gets loaded, and then finally you get your object back. And the same game is played for save, but it's in a slightly different order. So this time we save the data for each class going down the hierarchy. Okay, so let's do that, but with let's make it a simple array type. So this is an array object. All it's going to contain is an array of a specified shape. So we include as a KW-arg array shape. You can pass a default parameter if you like. And inside the constructor, we're going to initialize self.data as a NumPy array of zeros. But now we have to think about how we're going to save and load the data. So that's where save object implementation comes in. So we're going to write, we're basically just going to open a data.pickle file, and we're going to dump our data with dil and write it to that file. Same with load. We're going to open that file and read it out. If there's an exception thrown in these steps, you'll notice that the save and load have return a Boolean. This will be caught by the meta classes, and it will raise either an exception, or it will say, it will give you a warning if there is a problem loading some component. Okay, so this is the definition. So let's try it out. We're going to create an object with an 8x8 array, let's say, and now we can inspect that object. So if I remove that, you can see we get an array of zeros with the NumPy array, like we expect, right? And we can just get its shape, and it'll match. Okay. And now we can modify that object. So I can just take the 0, 0 component and like change its value to 50, right? All right. And now it's saved to disk. So here we're going to save in a different file, test object.dry. Okay, it succeeded, so it gave me a true. And now let's load it into a new directory. Well, we use load object to create a new object using that that serialized data. So in this case, now we can check that the data is equal. So we're going to use the NP-all comparator here. I'm going to use the equal sign, and it'll fill the array with a Boolean in every element of the array. And if any of them aren't equal, it'll raise an exception. And it didn't. So we can see, and I'll double check here. That the right value is in the right place. Okay, but let's look at the definition. So in this case, right, we've got array shape as a KW args. There were no arguments passed. There's a dry ID, and we've got a creation time. Okay, we can get a definition of that. But now it's important to remember, like, we can use this definition to build a new copy, just like we did before, but it's not going to know about the data that we changed. So you'll see the new object has 0 in its place, and that's because there's no data backing it yet. Okay. We can also do nested objects. So objects can take other objects as arguments, and this allows us, this really unlocks the possibilities of creating compound and composite objects. So we can basically contain the object we made before. So before we had this data object, which just takes one argument, and we've got an array object. So we create an array. We can create a new object, array data container, which takes that array object. Okay. We can verify that the container has the right value. So we can look at its first argument, and we can check its data and then check the assert that it worked. And yes, it does. So it's saved this particular container, this particular data array into the container at the right spot. All right, we can save it to disk, and we can load it from disk. So I don't have to remember how I created the object. I can just load the object from disk and check that, when it loads a compound object like this, it'll go through the tree of, like, it'll look through your arguments, and if it sees that you've got an object, it'll first construct that object. So it'll load its subordinate objects first, and then it'll create the main outside object. And in that way, it's able to correctly grab the 50 from disk. And these are both be new objects. So let's just inspect that. Okay. So this is an array object. That's right. It's got an ID FF4A. So that's the one that was saved to disk. That's the ID that was saved to disk. Let's just check up here. The array object we originally used had the ID FF4A, but you'll notice that they do have different IDs, the Python IDs. Right. So the build knows the load from disk is going to create new objects for you. There are some caveats to this, but I think it's a little bit too much to get into right here. It's, when you have to deal with nested objects, things get complicated quickly. And I do have, the load object does have some support for recursive loading, or like you can refer to a repository. So I mentioned already, we're going to get into repositories here in a minute, but if you've been creating, to see you've got a Jupyter session going and you've been creating a bunch of these objects, you can load an object from disk, but also point to a repository you have open And then rather than reading directly from disk, it'll try and load an object from the repo if it finds that there's a matching ID. Okay, so finally we're at the repo. All right, so I call it, repo is the object store and selector is the object finder. The diagram looks like this. You've got a repository, and inside there's essentially a box with a list of objects, or I think it's a dictionary in some cases. The goal is to make it so you don't have to load all these objects into memory. So a lot of times there's a special class called object file, which is just pointing to a location on disk, and maybe it loads the definition on there. So you can do selection on the definitions, but you don't have to load it all from disk. So repo implements a get function, which takes a selector, and all a selector is a class, argument, and KW args. And this can be nested. And they can all be callables. So if you pass a callable to class for selector, you can make a complex function. So let's say I'm interested in classes of type A, B, and C. You can make a special callable that does that and will return true if it's one of those types. So you pass that callable into class, it'll use that callable to determine whether a given object definition matches. Same with args and KW args. You can pass callables in there too and create your own complex selection functions. So you pass the selector here, get goes through the list and returns a simple list of the objects that matched. You can use add object to pass in an object and it will be added to the repository. So let's just create that. So we can create a repo with like this. We can also pass a directory into repo and it will point to a specific directory. I think without that, it'll I think without anything, it doesn't point to a directory by default. So let's test it out by, we'll generate a bunch of, we already have an array function, so we'll use that. We'll generate a bunch of arrays of different types and add them to the store. So I create 10 of each type, for each size in the progression. We create an object, maybe we initialize its data to some random state, and we add the object to the repository. Length is implemented for the repo, so it'll just tell you how many objects are in the store. So in this case, it's 40. All right. And now we can build a selector. So here in this case, we're going to say, we're going to look for classes with class array and that have KW args 20, 20. All right. So let's call get with that selector. And we've got a list, and we can just check to see. We'll map over that list. We'll just grab the shape of the data for each of the objects in the list, and you'll see there it is: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So this allows us to make some requests on what the shape of the data should look like when we go through the repository. Maybe we've got some opinion on how many layers our model should have. All right. So in that case, we can grab the first object. We can get the ID. And then if we have an ID, we can also search, we can create selectors that look for a specific ID. So if we know the ID, like let's say on one day you trained a good model and you save the ID somewhere like in your notebook or something, and you want to get that model back. Well, you just grab the ID and you can come in here and pass it under KW args, and it will just grab the ID of interest. And there you go, it got the right object. And you can also go directly, you don't have to go through selector. There's this nice helper function, get object by ID, which does the same thing. Okay, so that's objects and definitions, and then repositories and selectors. So these are kind of the basic components of the serialization part of DRYML and the composability part. So this is the way we can build complex objects that contain other objects. So the thing to do is, I would say you should close your kernel I'm going to shut this kernel down, and it'll matter more for future notebooks when we start actually using the GPU. But for now, I'm just going to close all my kernels down. So just to be sure, I've got a clean notebook coming in. So the next one is data sets. Let's see, I'll use OpenCV. All right. Okay, so again, the issue was each of these frameworks has their own opinion about how data sets should be, how data sets are done, like how, like, I know, for example, TensorFlow has TensorFlow data sets, and it has a particular API for fetching a particular data set. And once you get that data set, there's a particular way it returns the data set. And the goal of data sets is to kind of, once you've done the work of bringing a data set in, now you can just use it and throughout DRYML, not worry about different opinions about the way TensorFlow does it versus the way PyTorch does it. So the first thing to look at will be the NumPy data set. So it's an implementation of the API using just NumPy arrays and methods. So to use it, we're going to import NumPy data set from the .data, the data submodule. We'll create a random data set. So in this case, I'll say 28 by 28 to mimic the MNIST data set. And then we can create the NumPy data set just by passing the NumPy array. In this case, we're going to have to say supervised is false because we haven't passed a target data set, like a set of correct answers yet. So it's technically unsupervised. So that's why we say supervised is false. The first feature I really like about data set is the peek method. And this is something I feel is lacking in a lot of these frameworks. Just one simple method you can put on a data set to just grab the first element. And that's what this does. So it takes the first element out and then gives it to you, the user, to play with. In this case, because it's unsupervised and we gave it as one array, it's going to just return the whole array. So it's a 10,000 element array, 28 by 28. Okay. Next is batch and unbatch. So we've got our data, it's all in one big heap. We're going to want to batch it. So, okay, in this case, it's treated as batched. So we can pass the unbatched. You can use the unbatched method, and it will return a new data set that's been unbatched. Well, maybe we like that, but maybe we also want a batch of a different size. We don't want to have all 10,000 elements at once. So we can pass it through the batch method and pass that batch size, so 32. And we use peek again to look at the first element. And again, there you go. You see it's 32, 28 by 28. All right. And let's say we want to look at a specific example. So we can use unbatch to do that. So we take the base data set, we unbatch it. So now it's showing single elements. We use peek to get the first one, we get the shape, and that's 28, which makes sense. Since the base data set has 3 elements, three dimensions, we unbatch it and we get 2 dimensions left. This also supports take and skip. So you can take 10 elements, you can skip elements, and this is useful for splitting your data set up into training, validation, testing. You can also count the elements in the data set. There are heuristics to do a better job than this, but I provide a count element just in case you have a limited data set and you just want to check it. Count will try to physically count every element in the data set. That may not be a good or performant option for you, but until I'm working on the heuristic method to make this perform better. But for now, count exists and you can use it sometimes. As long as you don't have infinite elements. If you have infinite elements in your data set, it will take forever to count will never return. Okay, and then we've got iteration. So data sets can be iterated, and it works just like any other Python iterator. So we say, for element in the data set, and then we can say take 10 elements from the unbatched version, and we can print, we can use those elements inside the loop. So I'll take the 0th element of the, of the array, right? And so here we get all the elements that were created. All right, and now we have to go to supervised, unsupervised, and index data sets. By default, DRYML likes to have supervised data, and the way it's treated is there will be what I would call the X elements. So these are the elements you would pass into your model, and then Y would be like your target, so the correct answer, so or the labels to your data set. In this case, it's by default, if you have a supervised data set, you'll get a tuple with an X and then Y in it. If it's batched, you'll get those will be batches. If it's unbatched, they'll be single elements. You can also create index data sets, and that adds an additional item. So here I'm calling it I. If you've got an unsupervised data set, you're just going to get a tuple with the index and then the value X. If you have it supervised, it'll be I, the index, comma, and then the tuple X, comma, Y. All right, so here's how it works for supervised data. So we'll do the same game we did before. This time I changed the shape, and now I'm creating classes. So I've got 5 classes, and I'm using NumPy random choice to create those classes. So I create an X data and Y data, and now I can create a NumPy data set, but this time I set supervised as true. And now we can use peek like before and just take a look at the shapes we've got here. And just like expected, the X has the right shape, 10,000 and then 20, 5, and then Y shape is 10,000. We can do the same game with, if we didn't create an index for this data set, but we can make one by using the asIndex method. So asIndex will take a data set and it will create a new index that attaches to it. In this case, it's a supervised data set. So the first element of that tuple will be the index, and then the second element will be the X, Y tuple. And you can see the shapes should match. And let's just take a look. What kind of index does it make? So we didn't create an index originally, but so here we have the index data set. We unbatch it. We take 10, and then we take a look at the index. So .index shows just the index, and we've got. It's counting up from 0 all the way to 9. So that's 10 elements. That's exactly what we would expect. We can also remove the supervised data from if for some reason we're just interested in the X component. We can use as not supervised to strip the Y out of the data set, the Y component out of the data set. So we use peek to just take a look at the shape again. And now you'll see it's just the X component. So 20, 5, which we had before. All right. So data set also has a bunch of mapping and applying functions. So map takes a function and just applies it to all the content of the data set. So your map will need to be aware what shape it should expect the data to come in. And that's where we provide the apply functions as well. So apply will apply a function to both X and Y. So your function will receive the X and Y tuple, and your function will need to work off that. Apply X will, the function you give it should work on just X. Apply Y will work on just Y. And this allows you to simplify the process of like applying a small transformation, like maybe rescaling the X data to make sure it goes from 0 to 1. Map L is a special function, so you'll notice like the data that comes out of data set is a sort of nested tuple. You can also do dictionaries inside as well. So map L is essentially it goes through that nested data structure and applies a function to every single element within it. So here we've got like an index and then X and Y in a nested tuple. If you use mapL, that function that you give it will be mapped to every element. So you'll have f of d1 and then a tuple or like f of d2 and f of d3. So let's try the apply X. So in this case, we're going to apply square the elements of every matrix that is in the X data set. We'll peek and get the first element, and we'll use 0 to get the X component, and then we'll assert that the element we got, the squared element, is the same as squaring the one that we get from the naked data set, which it is. Okay, and now comes the framework transformation part. So in addition to all those functions I've discussed, dataset also implements a TensorFlow function, so .tf, which takes the original dataset and creates a TensorFlow dataset. So there's a TF dataset which implements the dataset API, but using TensorFlow iterators. In this case, here, if we peek now at the first element, you'll notice it takes a little longer than before, and that's because TensorFlow is starting up. And you'll look here, I get all these messages saying it's found all these GPUs, and now you'll see it's an eager tensor. The result of the first element of the data set is now an eager tensor instead of a NumPy array. All right, we can do the same thing with Torch. So the current data sets support the .torch method, and that transforms the data set into a PyTorch method. We can peek and look at the first type of the first element, and now it's torch tensor. And we can go all the way around. We can go here, we're going from TensorFlow to NumPy. So we can go from NumPy, originally this data set, we started as a NumPy data set. We'll go to TensorFlow and then back to NumPy, and you'll see the round trip. We're back with a NumPy array. Okay, so this allows us to go from one type of data set in one framework to another framework. Okay, so again, I'm going to close the, shut down the kernel for that notebook. And that's because, up here, TensorFlow got started and it allocated memory on the GPUs. So we kill the kernel and it should free that memory. All right, next one. This is compute context. All right. So I've mentioned before about the issue of these frameworks trying to grab the GPU. I try to remedy this with contexts and resource requests. These are concepts I made for DRYML. A resource request is just a dictionary that contains what you want, basically. So here, it's sort of nested. So the first level is the framework. In this case, your default is like no framework. TensorFlow is the TensorFlow framework, and Torch is the Torch framework. These are the three that we support right now. So here I'm saying, TensorFlow needs one GPU, and the other two don't need any GPUs. You can do more fancy stuff than this. You can say CPU/I or GPU/I to get a specific CPU or GPU. Now, I mean, currently I can't really do that. Like this, you can't really restrict a thread to one specific CPU, at least not that I know of yet. But the goal is eventually we'll be able to do that. You can do that with GPUs. Certainly with Torch and TensorFlow, you can say, I want to use a specific device. And that's what's going to happen here. You can say GPU 0 or GPU 1 or 2, and it will restrict your computation onto that GPU. You can also, for some frameworks, request a certain fraction of memory. So by default, I say, it's set to 1, so that's one whole GPU. But if you say 0.5 of GPU 0, it will, for TensorFlow, it's able to restrict the amount of memory that your models are capable of consuming on that GPU. So once you've got a dictionary, you can just use some helper methods to create a context. And then from there, all the TensorFlow stuff will be set up. But there's a helper function called context check. And this helps create barriers around your code. Like if you have a section of code that you think is going to allocate memory on a GPU, but you want to be sure that you're ready for that, you can put a context check and say, well, TensorFlow, and then the requirements that that section needs. In this case, I would say this one says it needs 2 GPUs. If I run this, it's going to fail. Oh, sorry. Okay, I forgot to execute this code up here. Okay. Here, it fails with a no context error, and that's because we haven't created any context at all. And so it's going to fail no matter what I put in here. All right. So that brings us to the compute context decorator. And this is where essentially the difficulty comes in when you're running, if you're running a TensorFlow model, you've allocated memory in the GPU, and then let's say you finished your training session, or let's say you want to try a new model in the same session. I think it's pretty much impossible to do that unless you're very careful with TensorFlow. But one way to get around this issue is to launch the whole thing in another process. If you search for this problem, you'll find that as a solution. So compute context decorator is meant to facilitate that. So here, compute context will, it takes a couple. This is more like a decorator generator. So it takes some arguments, and it has some behaviors, but a couple of important ones. First is the context that you require, so that like when you try to run the method, it'll check for a certain set of requirements on the context. Another behavior is to use an existing context. So if it's true, then it'll check to see if there's a context available, and if there is, it'll try to use it. And if it can, it'll just launch your method without making a new process. We also have don't create context here. So if we have the wrong context or we don't have a context, then in this case, it'll refuse to create, it'll throw an error and refuse to launch your method. Another one here is to update objects. And so you can pass DRYML objects to your method. And by default, if you make changes to that object in the thread, like let's say you're training it, those updates won't go back into the main thread. But if you set this to true, they will. The thread will communicate any changes you make to those objects back to the main thread. And then of course, we've got a verbose option, so it'll tell you a little more about what's happening. Okay, so to check to see how this works, I wrote a simple function here called check CTX. All it does is it imports the DRYML and it checks the context. So in this case, I'm going to check to see if TensorFlow is available. By default, because I don't have a context set yet, this will fail. And indeed it does, no context error. All right. What happens if I wrap it in a compute context decorator? So in this case, I'm passing it CTX-rex, which is what I defined up here, this little dictionary. And here I said 1 GPU for TensorFlow. All right. This is a new method, compute check CTX. And you can use this like a decorator as well. Like if you were up here defining it, you could have gone like this, compute context, right? And then pass the arguments in here. Or I also support, there's a thing called compute. I think it's just compute. That in that case, it says there's a set of defaults that are commonly used. Right, but if we go down here, okay, we create that wrapped function and now we execute it. You see it's taking a lot longer, and that's because what happened was the wrapper detected that there wasn't a context. So then it launched a process. And then in there, it created context to match what you requested. And then it ran your method. And then in this case, you'll see you got the message from TensorFlow saying it allocated GPU. And then it succeeds because that context had TensorFlow framework setting. All right. So you can set the current context. So like in the current thread, you can use the context.setContext method. And we can do that in the current thread. And now you'll see that the check context method works just fine. We can also kick the tires a little bit and say, what if I want 2 GPUs? and you'll notice this will fail. So context incompatibility error. All right, and then we can just double check that the original context we created works, which it does. All right, so again, I'm going to come over here and close this down because it's allocated memory on the GPU. And then we're going to go to number 4. All right, trainables. Okay, so we've got objects, we've got repos, we've got data sets, we've got context. So we can combine everything together now and get something that's really fancy. Within DRYML, all the machine learning model components are stored within the DRYML.models submodule. And again, the parts that are specific to certain frameworks are in the submodule of that. So we've got modules.tf for TensorFlow implementations, models.torch for PyTorch, models.sklearn for sklearn, and so on. We got also SGBoost. I think that one goes through sklearn. And essentially, trainables are these entity component system pieces. So trainable is like the base of that, is like the entity of that system, and then we can attach components to it, like a model or a training method, training function, let's say. We also have some transformations. So certain common data transformations can be incorporated to a pipeline. And that's within the DRYML.data.transforms. They are implemented as trainables, but these trainables have all been marked as trained, and that way they can be skipped during the training process. Okay. So for this notebook, I'm going to use GPU 0 and all of it. So we're going to set a context. All right. And you'll notice this is much easier to do than what you have to do for TensorFlow. There's like a couple of lines you have to do for TensorFlow. This one is just one line. All right, so we'll show how you would normally do training with a traditional framework. So we'll just use TensorFlow. This is the one I know best. So here we're going to load MNIST data. We use the TensorFlow data sets to load, and we've got supervised data. We're going to shuffle them, and we've got a train test split. All right, we're going to make a simple model, a sequential model. We've got convolutional layers, we've got flat, and we've got dense. We're going to compile it. So we're going to include a loss function and an optimizer, and then we can train it. And so I think people will be familiar with this step. All right, so that works. And we can then check its accuracy. So we can go through the test data. We're using a DRYML data set. So we batch it, and then we can, for each X and Y, we can check basically what it looks like. So for X and Y, we pass the X through the model. We take the maximum argument, and we get the correct, the predicted value. Yeah. And then we can compute what fraction of them we got right. So it's got a 96.8% accuracy. Okay, so how is it going to work for DRYML? We're going to create a couple of components first. So these are objects which hold parts of the pipeline. So in this first one is a model object. This is a sequential functional model. So in this case, it takes a set of layer definitions. This is just like for a sequential. In this case, the first element of this list is the name of the layer that we're interested in, and then we've passed its arguments in a dictionary. And then we also have an input shape here. I could probably move this input shape as an argument up into this first one here, but for now, when I was first implementing this, I just did it this way. We also have a training method. So this is, I call it Keras basic training. This is, one epoch. Inside it, we'll call fit, and it will go for one epoch. You can tune how many epochs, and this is great for hyperparameter tuning, because as I mentioned, this is a DRYML object. Epochs is exposed as part of the hyperparameters of that object. So you can change it, and then rerun the model, and you can get training that does however many epochs you want. You can run a test experiment to see like how the accuracy of the model changes over how many epochs you use to train. There are other training algorithms. There's one I think that's like got an early stopping algorithm on it, but there's a number of options, and this is the kind of thing that like the user should implement, right? If they have a new method of training they want to do, they would create a new DRYML object to hold that training method. Okay, and so finally we create the full trainable. So trainable takes a model, it takes an optimizer. In this case, I'm using the TF wrapper. So this is a DRYML object which just takes a class and then some arguments, and this is useful for signifying that this object should be a TensorFlow, should wrap a TensorFlow class, basically. So we've got an optimizer, a loss, and a train function. Oh, right. No, I need to import that. Okay. Now we create the data sets. So here we wrap DS train and DS test in TF data set. They're supervised, so we have to set that to true. Before we train on each model, we call the prep train method. And this is up to the user. If you're creating a new framework, you need to make sure that steps required before you train are inside the prep train method. So for Torch and for TensorFlow, that's been handled in the implementations here. So we call prep train and then we train. And there it goes. All right. We can compute the accuracy of the model in the same way, but this time we can take advantage of the DRYML pipeline or datasets API. So in this case, we take the data set and we batch it, and then we pass it to the model's eval function. So in trainable, eval will take a data set and return a new data set with the model applied. So we do that here, and then we turn it into a NumPy since the model is implemented in TensorFlow. And now we can skip that step we had originally up here, where we had to do we had to put the model, apply the model to X, basically. Now we can use the NumPy argmax method on this output. We can then compute the correct, in the same way, what fraction of them we got right. Okay, 97% this time. Okay, so now we get to pipe. So pipe is really interesting. It's essentially like an sklearn pipe, but it's been powered up for DRYML trainables. Pipe, it takes a tuple of trainables. So essentially everything you pass in here needs to be trainable. So first is the model. Then here we've got the best category transformation. So I mentioned earlier that we have some implementations for common transformations. One of them is get the best category. So all it does is it's going to do this argmax thing up here. So first you've got the model, and then you've got the best cat step, and then the result. Now instead of having this shape with like 10 on the output or something, since models are going to show you like probabilities on each of the output classes, we would have to normally compute argmax on it. Now it's just going to have one element coming out, since that's already been done for you by this step. And now we do the same thing. We do the pipe eval, but this time we're missing the argmax. And look, we get the same accuracy. So, all right. Now here's another nice thing about DRYML. We've got a metrics submodule. So there are a number of metrics I expect, I encounter a lot in my work, and when I encounter them, I tend to add them. Categorical accuracy is a big one. So here we can just directly, we don't have to write this code at all. We can just directly run categorical accuracy on the pipe and then the testing. And then we get the same result. So this will work for any model. Pipe can be any DRYML compatible model here. So now let's do the same thing, but for an sklearn method. Normally, if we were doing this experiment again in sklearn, we'd have to maybe change the way the data was input, and like we'd have to spend some time writing functions to load the sklearn model properly. But since we have we already have a trainable implemented for sklearn, we can just use it directly. So in this case, I'm going to import sklearn neighbors, and we're going to use the k-nearest neighbors classifier. So the sklearn trainable takes just a model and a training function. So in this case, we've got k-neighbors classifier with 5 neighbors, and then we've got the basic sklearn basic training with let's say 1,000 examples. So in this case, with k-nearest neighbors, the larger the number of examples you give it, the more data the data is gonna bloat. So I kept it to 1,000 here. You can increasing this will make it do better. Same with the number of neighbors you're using. If you add more neighbors, it's going to do better. In this case, though, so now we go to the pipe. We can insert the model. We have the best category on the end like we did before. And we need to flatten the data as it comes in. So the data originally was in 2D. We just add a flatten step. And that's it. We train it just the same way. Well, I have to remember here, we should prep train. So like that, and then train. And now we can check the accuracy. 88%. So that's all we had to do to change frameworks we were using. Nothing fancy. We didn't even have to re-implement the data ingestion or like add any helper functions really. All right. So the same thing. We're going to go back over here. We're going to shut down that kernel. And we're going to launch the next one. Okay. So now we're up to model generation. So this is where the magic really starts to happen when it comes to object def. So we've got objects, object defs, repos, contexts, transformations, trainables. So how we're going to make this all, bring it all together. So we're going to make some training methods which take a model, a DRYML trainable, and create a data set, train the model, and then send the result back. And we'll do it in another thread, so we don't have to worry about changing frameworks at all in the main thread. So the way to do that, we're going to create a gen dataset function that's available for all of our methods to use. Because these methods are going to be executed from another thread, we have to make sure that they're written into a file. So here I'm using the write file magic here to write the definition of this gen dataset method to a temp module. So in this gen dataset, we're just moving all of the TensorFlow dataset stuff in one spot. And here I'm adding a context check. So if I try to run gen dataset in a spot where I don't have a TensorFlow context, it'll fail rather than actually allocate memory on the GPU. So that's the context doing its work. And here we're going to create train model and a test model method, and we're going to wrap it with a compute context. In this case, we're going to say update the models. And then here, because the test method is not going to actually change the model, we don't have to do anything special, so we can just resort to the default wrapper. So in this case, we're using the decorator form. And you'll see here, we grab the gen data set, the thing that generates the data sets. We create the train data set. We use prep train and we train. In this case, the changed model will be propagated back to the main thread. And in here in test model, we pass it the model we're interested in. We import the categorical accuracy in the gen data set. We get the test data set, we prep eval, and then we evaluate the model on the test data set. Okay, what happened? All right, okay. I didn't execute every cell. There we go. So let's build a couple of classes using object definitions instead of actually creating them directly. And this will create a set of nested object factories to build up a full trainable. So here we're going to create some, get access to some components. So in this case, we need models, we need data, we need sklearn models, and we're going to use sklearn first. So we're going to get the neighbors directory, the neighbors module. So the first thing we're going to do is we're going to create a flattened definition. So this is that flattened step from before, but instead we're going to put it as a definition. So the object definition takes a class first, and since we're not passing any arguments, this is all we have to do. We're going to have a flattened definition and a best cat definition. And we can just take them and use it wherever we want. And so to build a sklearn model, we're going to build a whole pipe. So we've got object def, we've got the pipe class, we've got the flattened step, so this definition from before. We've got the best cat step from before, and then here we've got the trainable. So we've listed the trainable class. We have to create another, so you'll notice this is nested. There's an object definition within an object definition. And same here, we've got a model, we pass an object definition. In this case, it's k nearest neighbors, 10 neighbors, we'll say. And then we've got a train function. I've passed some additional arguments to the train function, and that's it. So now we can say we need some simple TensorFlow. We need to have a TensorFlow requirement, and that's because the input data set uses TensorFlow. But then from there, we can use build to create a new model, and then we can pass that model to train and test. Notice I'm overriding the requirements here with call context requirements. So now it's going to another thread and it's launching the training method. So first, this one will be for the train model, and then once it trains, it'll launch another thread for the test. And there's the result of the test, 80%, which is about what we had before. All right, so now let's go to the next step. Let's create a couple of models of the same type, and then we'll check to see how their accuracy varies over the course of training, like at the end of training. So we'll create a function which trains multiple models. We'll pass the definition, the number to train, and then the context we want to use. So at each iteration, we build a new copy with build. We train the model, we test it, and then we append the results and we send them. That's it. So we'll train 5 objects. Well, I'll lower that to like 2 because we're going to be waiting a while otherwise. It's like a minute per thing. So you can, in your own notebooks, you can play around with this. So I'll launch this. This time it's gonna, one at a time, it'll go out and train and then test. All right, that's it. Then we can now do statistics on those accuracies. So we can see it's getting about 81%, very close to that. All right, so we can do exactly the same thing, but with TensorFlow models. We just have to make a new model definition. So here, this is the same game we played in the last one. This time we're writing that model and trainable as an object definition. So we've got the model with a sequential functional model. We've got pipe, we've got the trainable here, we've got our optimizer, our loss, our category. And then I forgot to execute this one. Then we do the same thing. We just pass it directly to train multiple, and it will just go on its way. In this case, I'm saying to use the GPU. So I'm saying use GPU 0. And you can change that if you want. You can say use num GPUs as 2 or 3. And the way that this context implementation works, in this case for TensorFlow, it'll create a distributed or a mirrored strategy for your GPU. So if you give it like 2 or 3 GPUs, it'll mirror your model across the GPUs. Okay, I think that was it. Yeah. So now we can get the accuracy, and we're now like 97%. So this is doing a little bit better. All right, we can do exactly the same game, but this time with PyTorch. So here, let's see, I think I had to, yeah. So in PyTorch, you have to play a little more, little fancier game, because the optimizers in PyTorch, they want a reference to the actual model. And the way I handle this is that object definitions are capable of recognizing a nested, like if an object def occurs in multiple places within this nested definition, it will recognize that and create the same object and link into the same spot. So first we create a definition for the model. In this case, it's a sequential, and I'm using the same structure as above. So now here we've got the pipe, we got transpose, we have to cast here to float 32. But here we've got the trainable, the torch trainable. We've got the model. So this is the model def that we created before. And then we have the train function, but the train function takes an optimizer, and the optimizer wants a reference to the model. So I pass the model def in twice. Because it's the same object, DRYML will recognize that. And when I go to build a new version of this using this object definition, that this will be the same object in the end. And then finally, we have to use torch device CPU to get it back on the CPU, and then we can use best category. Okay, and then here we go. Train multiple. Yep, there it goes. It's training. No, it is done. There we go. So we can compute the accuracies here. Yep, 97%, just like before. All right, so we use the dry definition to create a template, a model template, essentially. And then the build factory function allows us to create new copies of it. And then we can train multiple versions. We can just, and using the context, we can switch between frameworks without any problem. I did not have to stop and start this Jupyter notebook once. So same thing, I'm gonna shut down this kernel, and then we're gonna launch the last one. Right. Now we get to hyperparameter searches. So basically I've combined the object definition with the Ray tune system to conduct hyperparameter searches. So the way this works, so first we're going to import Ray and we're going to initialize it. In this case, I've got in my job here, I've got 4 GPUs. I don't think we need 8 CPUs here, but I'm doing it just in case for the moment. Okay, so we've initialized Ray. The way this works is we have a prep method. So the prep method's job is to expose all of the needed little helper functions to the Ray trainer. So in this case, I've got repo gen. So this one creates a repository and points it to the model directory. Data context generator, this is useful. Right, yeah, the trainer needs to be able to execute this and get a context that's needed. We've got the model generator. So this model generator takes the config from the tune and uses it to build a model. So we use object defs to create the structure, and then we use .build and then pass the repo in, and then the build helper function will then either construct new objects or it will look in the repo to see if there's one already there. And then, yeah, finally we return the dictionary with all of those generators. So here we start the base stuff. So let me just, okay. First, we create a repository pointing to the model directory. We create it if it's not there. We create a couple of things like best category. So here I create best cat definition. And then here I'm using the get method, but I'm using the build missing def functions. So you can say get a certain object, but if it doesn't find it, it'll build one for you and then save. So now the repo has a copy of best cat definition in the repository. And this way, when it goes to get this best step here, where's best step? Yeah. So up here, within the model generating method, like once we're in the array thread, it's going to construct this best cat definition. It's going to search its repository for that category, for that particular definition. It'll find the step we've already created, and that way we're not going to have a bunch of these steps, just literally a bunch of these step functions littering our repository. Okay, so we say best cat def, we build missing. All right. Did I do that? Yes, I did. All right, so now we can run the experiment. This isn't necessarily a tutorial in Tune itself. So I definitely think you should go to the Tune, RayTune documentation to find out more about each of these. But essentially, we create a config space. In this case, I'm saying we're gonna do an experiment across kernel size. So we're going to do a random integer between 3 and 8 for our experiment. We're going to have a link to the local directory. We've got a trainer. So this is where prep method is. We have a trainer method. This is going to get passed into Ray, and it will orchestrate the experiment. So it'll call all of the repositories, use all the generators that we wrote, and it will set up the DRYML environment, and then it will run the training. In this case, we're going to pass a metric, with categorical accuracy. So that metric will get run. All right. Then we call tune.run with the trainer. So this is a training object, the configuration metric. So this is the metric we want to maximize. Resources per trial. In this case, I'm saying 1 CPU, 1 GPU. Number of samples, I'll say 20, but you can play around with it on your own. And then we just execute it. So here you see we've got some information now about all of the trials that it's going to run. And you'll see it's now running 4 at once. So I've got 4 GPUs. I said 1 GPU per trial. So now it's running 4 GPU training sessions at once. And this is a bit of a mess, this output here. So at least when you're running a lot of training at once, you should probably just pay attention to this section up here. So you can I'll zoom out just a little bit so we see the whole thing. So we've got all kinds of information out of Ray, like how long this trial has taken, current accuracy. And so these are finished. These are the accuracies that were achieved by each of these trials. So now it's doing 4 more. And you'll notice that some of these are going to take longer than others. Like the kernel size, the bigger the kernel size, it's going to take a little longer to train because it's a larger, physically a larger model. About halfway at this point. This is nice. It also tells us what the best trial is right now. And right now it's kernel size 4. Usually I think kernel size 5 is the one that gets the best value. Oh, I lied. 4 is usually the best one. It's just from last time it's 4. All right, almost done. Okay. Now we can inspect the data frame. So the results data frame, right. So the results data frame gives us access to, within a data frame, we've got the trial ID, we've got the dry ID, which is set by the trainer. So we can use this to get the actual model back out of the repository. And its final accuracy. So let's do that. So we've got the best trial ID here. We'll use it to see its data. So this is kernel size is 4. All right, same as the last round. So 4 seems like the best option. And here we'll get its accuracy, and we'll get its accuracy and ID. And then we're going to load the objects from directory. So repo, our version of repo hasn't changed the whole time. Like we just sort of created the repo and then we launched Ray to go do its thing. So now we have to update the repository with the new objects that have been created since we started. So I use the load objects from directory method to do that. So actually now we can look at the size of the repository. You'll see there's 120 objects in there. We can get by ID the best model. So we just grab that one right out of the repository. Then we create another test model method, and we can verify the accuracy. And there it is. And then let's take a look, 0.9803, and up here, 0.9803. So we got the exact same model back out. Okay, and that concludes the tutorial. We've got objects, object definitions, repository, context, trainables, data sets, and then integration with Ray to do hyperparameter searches. Again, feel free, let me go back to this slide over here. Go to the GitHub repository, raise issues if you find them, and then I'm always happy for better implementations of what I got. So PRs are welcome. Thanks for listening.